Hello, everyone. This is our latest findings on how structured linked data can help you be more visible in AI search.
The modern web is highly structured. Data exists in precise relational formats. But as generative AI takes over search, a structural blind spot has emerged. Traditional search engines actively parse semantic markup, like JSON-LD. JSON-LD is a script format that encodes linked data to provide machines with structured context. Search engines extract that code independently from the text to build dedicated relational knowledge graphs. Modern AI search relies heavily on retrieval-augmented generation. RAG is an architecture that grounds large language model outputs in factual, retrieved information. However, these pipelines typically ingest web pages as a single, flat chunk of unstructured text. When a vector chunker indiscriminately slices that flat document, it shreds the JSON-LD relationships. The structured code is broken into disconnected text fragments. In systems like Vertex AI or standard lane chain deployments, that structured metadata becomes just another string of text competing for limited embedding space. Technical SEO professionals often assume their standard schema.org markup guarantees visibility in AI search. The data shows it does not. To maintain search visibility, we must redesign web documents from passive text into traversable, agentic layers. The underlying data of the web has not failed. Our presentation of it has. If AI agents read the web like flat text, we must build structures that force them to recognize the relationships. A recent controlled experiment tested how well AI agents extract facts from different web document formats. The baseline condition was a plain HTML document, completely stripped of semantic metadata. The treatment condition took that exact same HTML document and embedded a standard JSON-LD script block in the header. This chart illustrates the results. Adding standard JSON-LD markup to plain HTML yields a statistically negligible accuracy gain of only 0.17 on a 5-point scale. Without dedicated parsing infrastructure, the large language model cannot extract relational utility from a flattened code block. If embedding raw code does not improve retrieval accuracy, we need to locate the specific structural changes that actually trigger an LLM's reasoning capabilities. Relying on standard metadata for AI search visibility is an illusion. Publishers must actively design for machine discoverability. Standard RAG performs a single pass of retrieval. Agentic RAG employs multi-step autonomous reasoning. This flowchart displays the architecture of an agentic search system. User queries are processed by an agent that orchestrates multiple external tools to build an answer. The engine driving this is the React loop. The React loop is a prompting framework where the agent continuously cycles between reasoning about what to do next, acting on that thought, and observing the result. The agent relies on the Search Documents tool for basic semantic retrieval, pulling text chunks from a vector database. Its most critical capability comes from the Follow Entity Link tool. This allows the agent to execute multi-hop traversals, moving across the knowledge graph from one related entity to the next. An agent cannot utilize this traversal tool if the document structure hides the pathways within unparsed text chunks. An AI agent is constrained by the tools it can deploy. It cannot execute multi-hop traversal without explicitly engineered pathways. We bridge the gap between human readability and agent discoverability by constructing an enhanced entity page. This graphic compares the two document formats. The left side shows what a standard RAG system encounters, a dense wall of unstructured HTML text. The right side shows the engineered solution, actively exposing navigational affordances to the AI agent. We begin by adding explicit schema.org type breadcrumbs. Schema.org is a shared vocabulary used to explicitly tag and categorize structured data on the web. These breadcrumbs instantly map the hierarchical context for the LLM. Next, we expose related entities with visible programmatic links right in the interface. These are dereferenceable URIs. Dereferenceable URIs are web addresses that allow machines to programmatically request specific data formats, like JSON-LD, instead of standard HTML. Finally, we explicitly embed system prompts directly on the page, giving the agent precise instructions on how to extract the logic. This chart tracks the resulting performance data from these combined structural changes. Plain HTML produces a dismal factual accuracy score of 1 out of 5. The enhanced format achieves a perfect 5 out of 5. The data reveals a counterintuitive finding. Agents using this highly structured format execute fewer tool calls because the initial context is so dense and readable. By combining human-readable text with explicit navigational affordances, we transform a static web page into an actionable memory layer, increasing AI accuracy by nearly 34%. Optimizing retrieval mechanics highlights a deeper ethical requirement for the future of the web. A decoupled architecture, where human text and machine data are served separately, creates a severe vulnerability. This separation invites adversarial manipulation. Bad actors can silently poison the AI's data stream, while the human-facing web page appears completely normal. Data trustworthiness is an absolute necessity as large language models synthesize reality for users. The enhanced entity page relies on a coupled architecture. The AI agent and human user pull information from the exact same unified interface. Coupling structured data with visible HTML creates an involuntary accountability mechanism. Corrupting the machine data instantly corrupts the visible human interface. If a publisher alters data to deceive an AI, they must simultaneously break the human experience. This establishes a single source of truth. Firmly, building for the agentic web requires a structural commitment to maintaining a shared, verifiable reality between humans and machines.